Hi, I'm Anna, and this is my Lab 3 magnetic field of a bar magnet report. Introduction. The purpose goal of this experiment was to determine the magnetic dipole moment of the magnet using the experimental data. It was also to calculate the distance dependence of the magnetic field of a bar magnet using both on-axis and off-axis magnetic fields. The magnetometer app Teslameter was used in order to measure the magnetic field at multiple locations. The Atlanta net magnetic field is approximately probably 49 microtesla. The fundamental physics principles used in this lab were the Biot-Savart law and the distance dependence equation, both of which are shown below. In the distance dependence equation, B bar is the magnetic field due to bar magnet, K is a constant, and N represents the distance dependence, which is the value we're looking to find. A summary of my results. The distance dependence was calculated to be negative 2.9921 meters, and the magnetic dipole moment of the magnet was calculated to be 1.93 am squared. General procedures for this lab. 1. Find location to do experiment with little to no metal in the surroundings that would affect measurements. 2. Download Teslameter app. 3. Calibrate magnetometer to magnetic north. 4. Locate magnetometer chip within phone. 5. Measure distance on axis field needed to obtain an x-component magnitude of 5 different microtesla values. 6. Measure off-axis field values. And once again, the net magnetic field observed in Atlanta is approximately 49 microtesla. This is my data taken. As you can see, it produced a relatively linear slope. So this equation we use on the next slide to calculate the different values. The equation given provided by the graph was y equals negative 2.9921x minus 14.766. The slope of this line represents the distance dependence, so n is found to be negative 2.9921 meters. To get an equation for mu, I rearranged the Biot-Savart law to find the equation below for a magnetic dipole moment. Mu equals k over 2 times mu naught divided by 4 pi. From the linear slope equation found above, I used the y-axis of negative 14.766 as equivalent to ln of k. Assuming that this is ln of k, k is found to be 3.87 times 10 to the negative 7th. Using the mu equation above, I then found the magnetic dipole moment to be approximately 1.93 am squared. Observations. When the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Generally, the magnetic field due to the bar magnet decreases as distance increases. This is my code, as it was used to calculate a model. Here's the model created by the code and the multiple calculations that the code performed. And on the next slide, I will compare those to the calculations run by the Excel sheet. So comparisons, the value of distance calculated by the Excel sheet was approximately 0.2526 meters, whereas the distance calculated by the code was 0.2527 meters, so pretty close in value. The magnetic field at 45 degrees was calculated by the Excel spreadsheet to be approximately 1.62 times 10 to the negative 5, 1.75 times 10 to the negative 5, and negative 1.2 times 10 to the negative 5 Tesla. Whereas the magnetic field at 45 degrees that was calculated by the code was calculated to be 5.98 times 10 to the negative 6, 1.79 times 10 to the negative 5, and then 0 Tesla. So the x component is calculated to be within one order of magnitude of the actual value. The y component is fairly close, being only approximately 0.04 times 10 to the negative 5 off of the actual value, but the z value is a little bit farther than the other two. Questions, conclusions. The first question was, what if you hadn't oriented your experiment to compensate for magnetic north, and instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? I believe that the graph would look the same, as it would not change how each data point is related to the rest, but it would cause a larger discrepancy between the theoretical and experimental data. The second question is, what if you were to stick two identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? I think that I would expect the magnitude of the magnetic field to be doubled. And that is the end of my report.